Hi everyone, hi, I'm Alex Danilo. I used to edit the HTML spec at W3C as part of my dark past. Right now I'm a software engineer on the Chrome OS team. And one thing I'm really into is this thing called WebAssembly, and you've hopefully heard about it. If you haven't, you're here now and you'll hear about it, and maybe you'll walk away with a bit more knowledge than you had before you walked in the room. In any case, I'm just going to cover a few little things like what is this thing called Wasm? I mean, what it really is about. Some of the technical nitty-gritty, kind of all deep down in the guts of it and how it works and how it hooks into stuff. The most important thing is why it matters, and like I was going to say this, there's another talk going on in the other room, the bigger room. All those people should be in here, right? Because it's a hugely important technology for mobile and the future, and the people in that room listening about some Dart thing don't realize they're missing out. Okay, and I'll talk about what's coming later on in the future of WebAssembly and some of the stuff that's on the horizon. So the first thing is, it's a binary format for executable code. So if you can think of it as a binary format, like, you know, when you have a machine like your laptop or whatever and you run an application, it's inside there is binary. It's like x86 instructions. Or if it's on your phone, an app, it's ARM instructions. And so this is really a binary format. So it's not JavaScript, it's not like curly brackets and stuff, it's actually instruction bytes. And so what it is an instruction set for a virtual stack machine. Now, does anyone know what a virtual stack machine is? All right, excellent. Nobody. Perfect. CS 101. It's between me and beer, so like, listen and learn. I'll ask you this after 2 beers. So a virtual machine is like modeling a CPU. So if you have an x86 CPU in your laptop or whatever, or your ARM in your phone, like, it's a thing that takes instructions, that reads the instructions from the memory, executes them on the CPU, and then it changes the memory outside, or it changes registers inside the CPU. Okay, so a virtual machine is an imaginary machine. So it's not an x86, it's not an ARM, it's just a design for a machine like kind of the ultimate machine, the ultimate answer to the question of life, the universe, and CPUs. Right, so it's the instruction set for that machine. So it's things like add 2 numbers and give me the result, or multiply numbers, or grab a chunk out of memory. So they're little basic stupid instructions, and that's what every CPU has inside it. So a virtual machine, an instruction set for that, is just one of these things, but more abstract than what you have in your machine. So it's actually a spec at the W3C. I said I did a lot of, I did HTML spec editing and a few other standards. The W3C, who knows what the W3C is? Yes, win. Okay, so the World Wide Web Consortium, they basically oversee specs that we stick in the browsers and all this kind of stuff. So WebAssembly was actually built in what's called a community group. So in W3C, you can come up with a community group or a working group. And working groups are all formal, and you sit around the table and you fall asleep and you vote on stuff. And a community group is like, hey, I've got this great idea. Why don't we start collaborating and iterating on it? And you can build anything you like, because it's not nearly as formalized. And WebAssembly was built in one of these. And then when it got to the point where browsers started to ship it, it moved over into a working group for proper standardization. And there's IP issues and reasons that you want to do that. But in any case, it's a genuine standard. So it's not some imaginary toy. But most importantly, I said it was in the future, and you know, the future is now, because it is in every major browser that matters. Well, maybe not if you're in China, but it's in Edge, it's in Firefox, it's in Safari, it's in Chrome, which also means if you use the Chromium code base, it's in Brave, it's in Opera. But the most important thing here, and the mobile people over there, if they can hear me, it's in mobile Chrome and it's in mobile Safari as well, which means that this stuff is available in something like 2 billion browsers in mobile phones today. So it's not a thing that you can maybe have a look at. It's not like sometime in the future it might be useful. Right now you can use it, and people are using it. So as I said, it's a compilation target for other languages. Okay, because it's an instruction set. Who here thinks you should write WebAssembly instructions by hand? Wrong! Well, unless you're a masochist, right? So we have one masochist in the audience, thanks. Yeah, so it's really, if you take something like C or C++, you can cross-compile it into a WebAssembly module and run it inside your browser. The Rust crew, the people that have the language Rust, like Mozilla's heavily invested in Rust, they can also compile to WebAssembly. So it's really something you take source code, build it into this binary blob module that then runs inside your browser. So what it is and where it came from is something that's important to learn. So has anybody heard of emscripten? Right. lot of people, very advanced. Now, this is a true anecdote. In 2004, I was sitting at Canon Research writing some code, and we had interns coming in, and we were like, what kind of stupid project could we give them? I know, why don't we write a C++ to JavaScript compiler? That'd be really cool. Then you could write C++ and run it in the browser. And we were just laughed at each other as like, what an idiotic idea. And then a few years later, some guy, Alan Zakai, comes along and writes this thing in Emscripten. And it's like, oh God, how dumb can you be? But Emscripten, when it first came out, ran about 150 times slower than the C++. Like, it was just a dog because it generated this JavaScript that JavaScript engines couldn't execute. So Mozilla and Alan came along and said, well, what if we just compile it down to this special brand of JavaScript? We'll call it asm.js because it's like an assembly language, and that'll be the assembly language for the web. And then SpiderMonkey, their JavaScript engine, could like detect it, and as soon as it detected it, it would go, oh, this is actually the output of the compiler, and we'll run a just-in-time compiler over this and generate fast machine code. And that became asm.js. And then all of a sudden they had this like really performant thing in the browser in Firefox. And then the other browser makers kind of looked at it and went, this is cool, this is semi-cool. I know in V8 and Chrome we kind of went, it's cool, but we don't want to optimize just for that. So what we'll do is we'll optimize for those kind of patterns so that even normal JavaScript will optimize well as the asm.js stuff. Meanwhile, in Chrome land, you know, some Google engineers are like, we want to build like the ultimate high performance thing that runs in the browser. So they came up with this thing called native client. And native client basically took a C++ program or whatever, compiled it into x86 instructions, and then put in special guard instructions and things to make sure there were no out-of-bounds accesses and memory problems, and shipped that as a module. And that was kind of running in the background, and you post message to it, and it would compute really fast. And in fact, that got to within 5% of the speed of true native code. But it wasn't portable. So then we came up with portable native client. Has anyone used that or heard of it? Right, one person. So portable native client was like, well, x86 is good and all, but there are ARMs and there are MIPS and there are all these other CPUs and Titaniums and all this. So what we'll do is we'll spit out LLVM intermediate bit code, which is like this abstract code, and then compile on the client side. But of course, this brought a whole lot of problems because what it meant was that the sandboxing of the executable, like you had to sandbox the compiler from the Pinnacle stuff into machine code and then check that machine code was legal. I mean, it was an architectural and engineering nightmare, which meant that no other browser wanted to touch it with a bar of soap. And so these two teams got together with Microsoft, with the Apple engineers, and designed WebAssembly. And so this is the irony. It's not web. Now, it's called WebAssembly, but it has nothing that locks it into the web. In fact, you know, it's just because it was developed in W3C, we called it WebAssembly. It's a cool name, it sticks, but there's nothing that limits it to that. Like, for example, you can run WebAssembly in a Node.js module. Now, does anyone here like remember writing C and putting it in CGI-bin on your server? Yeah, a few people. Well, see, the irony of this is we stopped doing that because it was unsafe. You know, it wasn't as secure as like, you know, Node.js or, you know, ASP.NET or whatever. But now, with WebAssembly, you can take your old CGI bin source code, compile it into a WebAssembly module, and load it on your server, courtesy of Node.js. So it comes a full circle. But not only that, the blockchain people, like, you know, this is a whole up-and-coming crypto community, they've decided that, hey, we need some kind of, like, you know, universal execution thing that we can, like, use for blockchain applications. So they've started to use WebAssembly in blockchain applications. In fact, there's some WebAssembly implementation called Wasm or something that runs on top of the Ethereum blockchain. So you can like compile your WebAssembly application, run it on the Ethereum blockchain, and lo and behold, you have some magical crypto thing that makes you rich. So, and it's not an assembly of nice donuts either, right? So has anyone used or seen assembly language? Right, quite a few of you. So it's binary, it's not assembly. It's actually nothing to do with assembly language. But there are kind of disassemblers that convert the binary format into a human readable form, in which case it kind of looks a bit like assembly language, but it is neither web nor assembly. And it's not a replacement for JavaScript. I have to drive this point home really hard. It is a complement to JavaScript. Right, this is the beautiful WebAssembly logo that was inspired by the notch in the top of an integrated circuit, apparently, according to the designer. So the whole idea is that it works with JavaScript. So right now inside a browser, you can't do anything with just a WebAssembly module. You have to load it from JavaScript. Any interaction with the DOM or externally has to be through JavaScript. So literally, it's kind of a thing that hangs on the side. if you think of it like on your computer, like you've got your CPU, that can be your JavaScript, and your GPU to do your high-performance graphics is your WebAssembly module. They're kind of complementary compute things that work together to give you the overall experience. Okay, so now we'll get into the awful technical detail to really like put you to sleep. See, this is the test. If you can survive this before beer, 100 marks. Okay, so in a traditional application, like the instructions that are running on your application or desktop on your phone, they can see all the memory, right? They can see all your local variables, they can see the stack, they can see the function calls, they can see everything. That's how debuggers do stuff. But in WebAssembly, there's a deliberate separation of memory space. So above here, there's your application, which is your WebAssembly thing that has that block of memory that you deal with. And down here is the virtual machine memory. And the most important thing is that thing on the right is the execution stack. Now, what that is, you know, when you crash or something in your web application or any application, you see a stack trace. Well, the reason you can see that stack trace is because that memory is visible to the executing program. In WebAssembly, that is hidden from the executing program. So there's no way that WebAssembly program itself can look at the stack trace. And that's deliberate, because when people write things like malware, one of the favorite things is to look at the nest of function calls and bash pointers and change memory, and then suddenly you're out in privileged memory or whatever. And so the execution stack's actually hidden away from the executing program. Now, the second thing is this indirection table for functions. So if you do a function call in a WebAssembly program, you don't kind of call an address. What you do is you call function 4. And then what happens is the runtime resolves function number 4, works out its actual address and calls it. So from your point of view, as the executing program, you don't know if you're calling inside yourself or out into JavaScript. It's all hidden through this indirection table. So if you do something like compile C or C++ to WebAssembly, what happens is you've got this block of memory, there's your addressable stack, you've got linear memory, whatever. All of the offsets, like if you compute things, all the offsets are basically 32-bit integers. And so you can sort of imagine this to be like a 32-bit pointer thing if anyone's done native code development. The reason these indexes are like indexes rather than actual addresses is so that when you're executing or accessing a variable or anything like that, you can easily bounds check it. Right? So you know the maximum size, you can go, here I've got an index into a piece of memory or an index to a function or whatever. It's one check to check if it's off the end of the memory that you're allowed to use. And so that makes it faster. Also, quite a lot of the implementations will stick a hardware break on each end of the block of memory that the WebAssembly module is working with. And so you actually get a hardware trap if you try to do something out of bounds. So by design, it's actually quite secure. But what's it good for? Like, this is all well and good, but what would you actually use this stuff for? Now there's a bunch of people doing it, like Unity and Epic. They've compiled their 3D games engines over to it. But a really good application is things like high-performance codecs. So has anyone seen Kenneth from Intel, Kenneth Christiansen or something from Intel, his work in this room? No? Anyone know him? Oh, yes, one person at least. I thought he was famous. Obviously not enough web famous. Anyway, Kenneth came along and he took the WebP decoder and compiled it to WebAssembly and shoved it in a service worker so that he could show WebP images working inside Firefox. And so from a web developer's point of view, if you do something like that, you can support image types in your browser that aren't supported by the browser. Right? So if you want to use WebP to reduce bandwidth, you can actually do it. And because you stick it inside the service worker, nobody knows. It's also good for video editing, like we had Phil talked earlier about WebRTC and what you could do with video in your browser. Well, WebAssembly is a perfect candidate for manipulating video inside your browser. And of course, one of the great things is there are thousands of code bases. Has anyone gone to GitHub and seen how many repositories and all kinds of stuff are out there? There are millions and millions of man hours invested in those code bases. And what WebAssembly does is it means you can take one of those code bases, cross-compile it, shove it into your web page. So if you were in the mobile room and you were writing Objective-C or something, or even C++ for some hardcore game, you could actually bring that and run it in your browser. So it's kind of like a migration thing. This is all part of the world of PWAs, and we're making browsers more like native platforms. And in fact, WebAssembly is a really large part of that. it's also good for supporting other languages. So at the moment, kind of the main 3 targeted languages are C and C++ and Rust. But there are other ports around. There's Kotlin, there's a Go port, there's a C# port. You can actually run the .NET suite of languages on top of WebAssembly. There's even Forth. I mean, there's all these languages, and they're all coming to the web. And that'll all shake out over time. A few favorites will probably appear, but the bottom line is it's a great compile target for anything. I spoke a bit earlier about the other embeddings with Node.js and blockchain, and that is truly frightening. There's also a bunch of people that have built these startup companies now who are using WebAssembly as like a distributed computing thing. So they have these companies where you effectively have data centers all over the world, and you buy compute servers. So you pay for your computes. And as the universal binary format, they basically throw around WebAssembly binaries around to these distributed things, and people bid on how much they're going to do the computation for you. So it's kind of like finding all these really weird applications. So we're in space now. It's getting closer to you. I can see people getting thirsty. But how do you use this stuff, right? It's really quite easy. You install the Emscripten SDK, and you basically do this. Here's my source program, hello.c. I go emcc, which is the Emscripten C compiler, and I go -o hello.js. And you're done. You've built a WebAssembly module. And does anyone see anything wrong with this picture? Apart from the lack of dark matter. Yes? Spot on, perfect. Yes, it's JS on the end. It's not Java, it's not WebAssembly. So what actually happens when you do this is it generates 2 files. It generates a .js file and a .wasm file. And what the JS file is the glue that loads the WebAssembly module for you and takes care of all the horrible nitty-gritty. So in fact, when you actually include this on your page, you go script source equals hello.js, and under the covers, magically the WebAssembly module gets loaded and you don't have to do anything. So excellent, great answer. So what actually happens under the cover is you can do all this explicitly. So this is what that hello.js will generate. Something like WebAssembly instantiate module bytes does all this magic under the hood. So you can do that manually if you want to, but I highly recommend you don't. Because unless you're right into WebAssembly, just let the compiler do it for you. It means the people maintaining the tool chains will fix bugs and make it all work easily. And very soon, they'll be available as ES6 modules. So the intention is that you can just load a WebAssembly module as if it was an ECMAScript module, and you won't know the difference. It'll all just communicate via the imports and exports. Okay, so very important thing is when you're actually building a module, they can only access their exports and imports via a predefined interface at compile time. So you need to think really carefully about your API. So exports are the functions in the WebAssembly module that you export out to JavaScript, so JavaScript can call, and the imports are the JavaScript functions you pull into the WebAssembly module. So JavaScript can call directly into your module, so when you load it, you can just call module, look at this property exports, and call your function directly. It's that simple. So to all intents and purposes from the JavaScript side, looks like you're just calling another method. It's quite simple. And what's interesting here is, of course, because you can import, the WebAssembly module can then call JavaScript functions, which can then call other WebAssembly modules, which can call other JavaScript functions. So you can literally get an interleave stack between JavaScript and WebAssembly. Right? So models like the native client thing were they were like an RPC mechanism. Like you post a message, you get a result back. They didn't work well. So this is not like an RPC kind of thing. This is literally, it's properly integrated as 2 runtimes working together. Now, a few of the bit of the terminology, probably should have done this earlier maybe, but every WebAssembly binary is called a module, which when you think of modules, you kind of think of ECMAScript modules, kind of makes logical sense. And the binary format itself was just defined with 3 really important things in mind. The number 1 is streaming. Now what that means is that the actual format was designed so that as you stream it across the network, you can compile it as it's coming into the computer. So if you had, say, a 10 megabyte WebAssembly module, and hopefully you won't, as it's coming to the browser can actually compile it so that by the time the load is finished, the code is ready to run. So the second thing is it has to be validated. So these instructions that come in, they have to be checked to make sure they're safe, so they don't do out-of-bounds accesses and all this kind of thing. So the format was designed that you could do that validation in one pass. So that means that the streaming comes in, the validation happens as soon as the bytes hit the wire, and you can go straight to compilation without waiting for the whole thing to load. And then the other thing was that it was designed for very fast compilation to native code. So it's very important that you could convert this thing into actual instructions really quickly. So the format is very simple to help that. And in fact, most of the browsers now, like We've shipped it, V8 shipped it, SpiderMonkey shipped it, what they have now is what's called a tiered compiler. And what that means is the first time these bytes come in, they do a really quick compilation. They don't try to optimize everything. And then in the background, kick off another thread to do a highly optimized compile. And then that highly optimized compile will run faster. Now, the reason they do that is to make startup speed a lot quicker. So for example, Unity, the 3D game engine, it used to take like 10 or 11 seconds to compile and get started, and now it takes less than 2. And so this is a huge win as far as getting your application up and running fast. Now the modules define a few things. They define functions, which are the things they export. They define globals, which are globally visible to the WebAssembly module, not global to JavaScript. They define the imports and exports, as I kind of said before, so the functions you export, the functions you're bringing in from JavaScript. And also they define the memory requirements. And so what's important to know right now is that WebAssembly modules are limited to roughly 2 gigabytes of RAM. And that's just for one module, which should be enough for everyone, right? You know, 640K used to be enough for everyone, so 2 gig should be okay. In fact, it's slightly less than 2 gig. But when you compile it, there are basically 2 things you can do. You can say, I want to have 100 meg, and that's all I ever need. Or you can say, I want my memory to be able to grow. And so naively, you'd say, well, I'd just say, allow the memory to grow, which is naive, because if you say you allow it to grow, that means every time you go to allocate memory, you have to do a test to see, oh, have I got enough memory? No, I have to grow, or yes, do the allocation, and that slows you down. So it's actually faster to have a fixed amount of memory. Now, the second thing is that if you have a limit of 2 gig, right, if you say, I want to have, like, you know, growing memory, and I'm growing and growing and growing, the moment I hit 1 gigabyte, so I'm halfway to my limit, the program will crash, because when you go to grow the memory, you suddenly go, I've got my 1 gig here, I try and allocate more than 1 gig to do the copy over to the bigger piece of memory, and suddenly we're above 2 gig and the whole thing crashes. Whereas if I'd said, oh, I need 1.5 gig and I don't want to grow, then my program would run forever, no problems. So very important to think about that when you're using it. We talked about the instruction set a bit earlier. It's a simple stack-based instruction set. Now there's no need, I know this is getting a little bit too technical, but when you design a virtual machine, you can either have a stack-based virtual machine or a register-based virtual machine. The difference is a register-based machine is like a normal CPU where there are registers, they look like slots that you put, you know, data into. And a stack-based machine, everything is on one stack. It's just like bang, 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 pile up the data comes back down again. Now the reason that the WebAssembly folks chose a stack-based machine was because they wanted to be architecture independent, which means how many registers do you use if you're going to have a register-based machine, because it needs to map to a real machine. And also, it's a lot easier to do certain compiler optimizations. And also, you know, in the next 20, 30, 40, 50, 100 years, people will come up with better register allocation algorithms. So you don't want to lock into registers at compile time. You want to let the JIT get better over time. We already talked about this. It's designed for fast validation and compilation. And that's a nice, I don't think that's fast enough though, 220. As long as, if that was miles an hour, it'd be okay. So, okay. Another thing is that this is the dumbest binary format on the planet. There are only 4 data types, right? There are 32 and 64-bit integers, 32 and 64-bit floating points, and that's all. And you're all looking, well, Tom's looking especially glazed over there. It's like, you know, how's this going to work? Because we do everything in strings in JavaScript, right? So this is useless to me. Well, in actual fact, how you do this from JavaScript is you take the WebAssembly memory, you map it to a typed array, you write your string into your typed array, you get its offset, and you pass that in as a number. So in effect, it's like a pointer to a string. So everything is done with shared memory between the JavaScript and the WebAssembly side. So this may seem like an extraordinary limitation, but it's not so bad. So let's just quickly have a look at an example of an instruction. Is a 32-bit integer add instruction. So the way it would work in real life, you'd have your stack over here, you have your 2 values that you've put on the stack somehow. The add instruction gets executed, takes those 2 values, adds them, and then leaves 1 thing on the stack. That's the addition of the 2 of them. So really simple instructions. So here's another example of loading a value out of memory. So these are two instructions. I'm loading a constant, 1024, and then I'm indirect loading the value at address 1024. And so the constant instruction puts 1024 on the stack. The load instruction takes that value and pulls it out of memory and shoves it onto my stack. So that's kind of how basic the instruction set is. It's really very, very small. So enough of my talking. Everybody needs a demo, right? Okay, so you're probably wondering what kind of things you can build with WebAssembly. And, oh, I want to do that. That is what I want to do. So this, folks, is the DOM. This is actually an SVG, would you believe? And so these little balls here, they're actually circle nodes. Has anyone used SVG in this room? A few people. Excellent. Good. So this is an example of a physics engine working through WebAssembly. So it's a physics engine called Chipmunk 2D, and it's used in a lot of a lot of 2D games. It's actually been in #1 things on the App Store. And I took the Chipmunk 2D engine, I compiled it into a WebAssembly module, and then I interfaced it to my Hourglass, which is just an SVG graphic, and each one of these balls is just a DOM node. And so what happens is every time request animation frame gets fired, it goes off into the physics engine, says, hey, where should all the balls be? Run your simulation, and then I reposition them all and repaint. And so you can even, click this and it spins around, and and the gravity does its thing, and it's just magical. But there's an example where you've taken an actual code base from somewhere else, so recompiled it, and put it to use there in your browser. So I'll do another little demo. Now, this is Phil, pay attention. Phil gave us a great talk earlier on WebRTC, and of course, Get User Media, which is our favorite. So yes, here we go. Right. So this is implemented using Get User Media. And of course, WebAssembly. Now, what the WebAssembly does is it actually it takes the stuff off the Get User Media, pulls the bitmap in, sends it to this WebAssembly module, which does all this weird image processing stuff. So you can sometimes they're really good effects, So it's actually possible to build a proper video editor. I can change lights. That's interesting. So this is just kind of to give you a little bit of the taste of the kinds of things that are feasible now when you've got Get User Media, you've got WebRTC. In fact, the WebRTC team inside Google have been experimenting with WebAssembly for certain applications inside WebRTC, but that's still on the horizon. So I'll just go back to that's enough demoing. Okay. Right, so you're all dying to get to go and get into WebAssembly, right? So the first thing you need to do is get the SDK. So you can follow this link if you want to take a photo of it, or you don't have to, because it's linked to from webassembly.org. So your best place to go is webassembly.org, which is the reference website. It contains links to documentation, demos, a lot of really boring technical stuff you shouldn't waste your time reading. But in any case, it's kind of the canonical starting off point to go and find things. Everyone got that? Good. Gone. Okay. So once you do all this and you want to go out and build something, it's very important to optimize your code because you want things to run fast. You want your users to have a great experience. And so one of the really good things to do is to actually shove stuff into web workers to run them on parallel threads and let the web worker do all the heavy lifting and shove your WebAssembly stuff in there if you can, because you already think it's computationally heavy, so stick it over there in another thread. Now, a company called Autodesk, who wrote this thing called AutoCAD, which is a 2D program that someone may have heard of in this room, they have a 30-year-old code base, and they compiled that 30-year-old code base into WebAssembly to run in the browser, and their architecture sticks the entire AutoCAD core library in a web worker. So they have the whole UI as kind of a JavaScripty UI, and it communicates with the web worker. So all the 30-year-old code running over there is just sitting on a parallel thread, and so they get really good response doing it that way. So, of course, you can pass different linker flags into the compilation. So if you use -03, that'll be your fastest kind of optimization, so things will run faster. Sometimes you may have problems, so you roll back the optimization to debug, but generally use -03. And then we have this flag called -OS with a little s. Now this is an interesting one. This is S for size. So what happens is, remember that we compiled and we generated a JavaScript file and a WebAssembly file. So what happens is that that JavaScript file by default contains everything under the sun, like it's hundreds of kilobytes. It's basically an entire library of C functions and interfaces and whatever, like interfaces to WebGL and all this kind of thing. -OS actually takes the generated JavaScript and the generated WebAssembly and looks at who's calling what and optimizes out anything that's not used. So it really shrinks the size of the output. And today you have a first, because Chrome 70, which has just shipped, is actually supporting native threads in WebAssembly. Does anyone know what native threads are? Right, one person. See, we never had proper threading in the browser. We had this thing called pthreads. And there's actually a blog post going to be coming out next week to announce that WebAssembly has threading support. So if I click on this, here is an example. If it loads, come on hotspot. Oh yes, all right. This is a C program with 4 threads, and each thread is updating its 2 characters, and they're running completely non-deterministically in parallel. So it's literally compiled, and the 4 threads are just going, I'm going to update my bit of the page in parallel, and there you have it. Nice as a little demo, but for things like game engines, for video processing, for anything like that, having true parallel threading is a huge win. And a lot of existing source code applications require proper threading to run. So it's a really good thing for future porting. Okay, so debugging. This is, of course, the pain point of all our lives. In fact, I used to kind of say to people, to engineers, young engineers, and it's like, what's the optimal number of lines of code you should write? Does anyone know the answer? 0, exactly. Because all we do is write bugs. It's the bane of my existence. But very important to know, if you are debugging with WebAssembly, as soon as you open DevTools, it doesn't run proper native code. So the way that debugging works is it actually runs an interpreter. So you can step over the individual instructions, but to do that, it actually runs in an interpreter. So even just having DevTools open will slow down your WebAssembly application. So if it's running really slow and you're debugging and you think, what have I done wrong? Close DevTools. At the moment, you can single-step instructions, but in Chrome 71, which is coming out relatively soon, there's full source maps access, so support, in fact. So which means that you can literally walk through your C++ code, do proper debugging. It's like a huge jump in the developer experience. And the future, just a couple of things that are happening. The SIMD instructions. Does anyone know what a SIMD instruction is? Yes, not too many. Okay, single instruction, multiple data. What that means is, say that you have an RGBA image. We all know what that is, right? Well, normally on a normal CPU instruction, you want to say, darken the pixel. You darken the red, then you darken green, then blue, then alpha. So you kind of do that. That's 4 instructions. It takes 4 cycles to execute. A single instruction multiple data thing does it in 1 cycle. So all 4 channels working parallel, and all CPUs support this. So this is really important in image processing and these kind of applications. So that's coming soon. There's AnyRef is another thing, the 5th data type. So what this is for, do you remember 32 and 64-bit ints and 32 and 64-bit floats? Well, it's the 5th type. And what it is it's a way to get an opaque handle into the WebAssembly module and then back out again. And the reason for that is that if I want to manipulate JavaScript objects and do stuff with it, I can't unpack them. I don't understand JavaScript objects. I may just want to take it in and pass it back out to another JavaScript method. So that's what the AnyRef is for. So I can say, take like an object in JavaScript, pass it directly in. I don't need to know what it is. And the WebAssembly module can just deal with it as it doesn't know what it is, and it can pass it back out again, and it all just works. One of the other things is this thing called host bindings. So right now, if you're in WebAssembly and you want to say create a DOM node, it has to go through JavaScript, create the DOM node, back through JavaScript, the other way, and it's all finished. The host bindings proposal is one that you can define an interface from like the WebAssembly side, that then the runtime goes, oh, he's calling this function, but actually I know that that has a C++ function in the browser, and I can just jump straight through and avoid JavaScript altogether. So that's the host bindings proposal. And garbage collection support is coming because there are lots of languages like Go, JavaScript, Java, you name it, that require some kind of garbage collection support. So native primitives to enable that are coming to it as well. So that's about all I have for you today, and I hope you learned at least one or two things, and we'll enjoy thinking about WebAssembly and the horrors that you can perform with it over a quiet drink. And any questions if you like.